Again, it's not a requirement, but this video provides some information about the structure of this course, so I still recommend to spend some time on it. PY 105 students spent about a couple of hours on online surveys, so it's kind of similar. And this is the question, two questions at the same time I would like you to answer. Right now, right here, the direction of the electric field. In the first case on the left, the electric field is generated by a positive charge, and a completely different case on the right when electric field is generated by a negative charge. So two answers at once. What's the rule? In physics, it's everything about rules. So you should say a rule. Could you explain it one more time? I'm asking you a question. What arrow should you choose to represent correctly electric field generated by this charge at that point? That's one question. You can ignore everything else. And a second question, well, which is technically the third, what arrow should represent electric field generated by this charge at this point? And electric field, again, is a slang. The full name is electric field strength of electric field generated by this charge at that point. That's a whole sentence. We need to know this slang because people use this slang in the textbook, homework, assignments. However, we also need to know what that slang means. For example, my nickname is Mr. V. That's a slang. It means Valentin Viktorovich Voroshilov. That's the full name. So, and here again, as anywhere else, we have to start from a rule. For what's good about physics, there is a rule for everything. They have different names. Some rules we call definitions. Some rules we call laws, and this is a definition, a part of a definition of a physical quantity we call electric field strength. So, anyone, please tell me the rule. Yes?
When it's positive, it points
That's it. That's the rule. If you know the rule, the rest is your ability to apply that rule, which based on, well, how good you are at drawings, for example. Yeah. And if I take a different point, let's say here, if I want to apply the same rule, I need to know what does it mean away. Well, technically directly away. Would it be directly away? So, a mistake. Would it be directly away? Another mistake. So many mistakes already. It's just 902. So, the directly away means you have to draw a line which connects the source, which is a charge, and the point. And then you should continue and add an arrowhead. That's what away means. And if you take the same point here, directly toward means, again, you have to enact a specific procedure. That specific procedure includes drawing a line which connects a charge and a point, and then you should draw a little arrow which points toward the charge. That's how the rule works. And we know the magnitude of electric field of a single charge is related to the magnitude of the charge. Technically, I should add these vertical bars to everything. And the positive charge and the negative charge generate electric field of the same magnitude. The equation is the same. That magnitude decreases when we move away from a charge, but the direction depends on the charge according to the rule. Well, so I'm going to give you a time to start working on this problem. It's a new problem. Now we have two charges generating electric field at the same point. Every time when we need to solve a new problem, there is always the same question we should ask first. What do you think is that question? Why do bad things happen to good people? Yeah? No. The question always is, have I seen it before? And we always have seen something similar before. Maybe not exactly the same, but something similar. And our brain is a very powerful pattern recognition machine supplied by the memory. So a lot of things in this room depend on memory and pattern recognition. Do you recognize this picture? So, what do? Well, if we have recognized something from the past, we just start enacting the same set of actions we've used. Sometimes they will, bless you, give the answer immediately. Sometimes not. But we always have a starting point. So when a student tells me, I don't know what to do, he or she is lying. You know what to do. Go to lecture 3, slide 9, and follow the procedure. That's the rule. Try to remember something similar from the past. Try to remember what actions have been used in a similar situation, and try it. The key word is trying. Trial and error. That's the only scientific way of achieving the goal, solving the problem. Normally, after the first or second try, you get some new information, some new physical quantity, which will allow you to make the next step. So there's always a question you ask yourself after making a step ahead. What can I do now? There's always something to do, including ask a question or give up. Don't give up. And you repeat it again and again, and eventually the problem is solved. That's it. That's a problem-solving strategy which works all the time. No exceptions. Now, and we have seen this situation. We actually have it solved. We literally have found the magnitude of a net force acting on a charge placed at that point. So we don't have to repeat this again. We can just use that information, right? Now, that's not what we are looking for in this situation. This is the net force. We need the net electric field. Okay, so now our brain starts searching for the connection between net force, net field, and the charge. If that search leads to the right equation, we're done, basically. So right here, let's try green. Right here, we have F net acting on a 2 nanocoulomb charge. And the question is, what's supposed to be net electric field at this point equal to? Force, charge, field. What is the relationship between these three variables? Exactly. So we can write it as a product, force equals charge times field, or in this situation we can rewrite it because we are calculating the field as a fraction. These are vector equations. We need just a magnitude. So we can add those vertical bars, and the magnitude of electric field at that point will be equal to 4 times 10 to the negative 8. And I just want to remind, it's a disclaimer, I'm not responsible for that number, she is. Divided by the charge 2 nanocoulombs. 4 divided by 2, 2, negative 9 becomes positive, 9 minus, so 20. And an equation tells us the unit, a Newton over a coulomb, a Newton over a coulomb. But of course, I want to resolve this problem just using electric field on its own, because it's also a problem which helps us to review how we use vector components in general. For example, this approach is not very convenient if we need to describe the direction of that arrow. Yeah. To describe a direction, we need to find some kind of an angle. And here, we just know magnitudes. So, any questions? Yes?
So where did the two clubs come from?
From lecture 2, slide 7.
Go back to the previous slide for a second.
Here we have two same charges which generate electric field at point P. At that point P, previously, yesterday, we had a charge of 2 nanocoulombs placed.
Already given. We didn't have to find it. Was it already given? We didn't have to find it.
The charge was given to us, yes. The charge was given as it was a part of the problem. We have solved that problem for the given charge. And now we don't need that charge anymore, because the electric field doesn't depend on a charge located at that place. So we need to extract the information about the charge. And extraction in medicine might mean very many things, but in physics it means division. Sometimes subtraction, but mostly division. Again, don't worry about it. We're going to do it again. You know it's going to be posted and taped. So, two charges generate electric field at the same point. Positive charge generates electric field, which is directed away from it. We can call it E1. Let's call it charge number 1, charge number 2. A negative charge generates electric field, and we know it probably stronger. which is supposed to point toward that charge. Now, just again, to refresh the equation for a single the electric field generated by a single charge, this is how we can calculate it, right? For the electric field, the constant is the same. The charge is 9 times 10 nanocoulombs, and the distance is, again, 3 times cosine 30 squared. You know what? The whole thing? Well, why would you tell me just the cosine? If you want to tell me, tell the whole thing.
The whole thing is 12 times 7.
12.07. That's a field, a Newton over a Coulomb. And for the second electric field, the individual electric field, we should do this, and that's supposed to be same constant, a different charge. What do vertical bars mean? Magnitude. So if the charge is negative, we don't write a minus. And now it's supposed to be 3 times sine of 30 squared. You see, this part of our reasoning employs our knowledge of geometry. So again, you should refresh your knowledge of geometry related to right-angled triangles, Pythagorean theorem, sine, cosine, tangent. This is the hypotenuse. This side is adjacent to this angle. This side is opposite to this angle. And the number is 16. Thank you. Now, if I want to do the angle, I got to use components. Each vector has components. But to do components, I need to introduce the reference frame. And actually, it's kind of handy to introduce it twice for each vector individually. For example, this vector E1. We know how long it is, 12.07. Now, a vector and components always form a right triangle. So this arrow, green arrow, represents the x component. And this arrow represents the y component. And together they form a right triangle. And if we want to use a triangle, we need an angle. So, do we know any angle in this triangle? Except 90 degrees, of course. We know that's 90, but now we need an additional. Bless you. So, do you know angle? Who knows? Please raise your hand. Yes, please tell me.
Isn't it 30? Are we nothing?
Which one? This one or that one? Right choice. You got it. Wrong choice.
I was going to say
Lower or top? The lower one. If we look at this picture, this is 30 degrees. So now we have to apply our parallel thinking to see this is 30. Same lines, vertical and angled. This is 30, which means this is 30. That's geometry. Well, this will be 60. That's geometry. So now we can, and that is E1. Now we can write the expression for each component. And this is not something new. This is a review. So x component should be equal to hypotenuse times cosine of 60 or sine of 30, it's up to you, which is 12.07 times sine of 30. It's about 6. The y component, please tell me what should I write for the y component. What do you think? What do you think? Is it correct? Is it wrong? The good thing about small room, everybody is reachable. So we have an expression. We have only two options. It is a correct expression. It is a wrong expression. If you think it is a correct expression, please raise your hand. You should raise it because you said it, okay? If you think it's a wrong expression, please raise your hand. Now, since you know it is wrong, you should tell me what do you think is wrong with this? We are writing an actual component. We're not calculating a length of a side of a triangle. A component of a vector is a vector. We remember that, do we? And for every vector, the component depends on the direction. We have a rule about that. What is the rule? Down means negative. Now it is correct. Now you don't forget, hopefully. So, negative 16 times cosine of 30, I don't know the number, please tell me. Negative 10.5. Since these are components of electric field, so unit is the same. And now we're going to switch to the second arrow. The second arrow also has two components. So first we need to draw that arrow. Something is wrong? Yes? That's her fault. My brain is running ahead of my hands. 12 times cosine of 30. Does it change the number? It should. You used 12. Okay, thank you. So negative 10.5. Thank you. Thank you, thank you. Thank me. So now we are calculating x and y components of a second arrow, and we know what to do because we have to repeat exactly same steps. First, we have to draw the components. This arrow represents the x component. This arrow represents the y component. We can connect the components. They form a triangle. It is a right angle triangle. And we need to know a certain angle. So in this situation, we may need to do some extra drawing, like what can I, maybe not. I know that's supposed to be 60. So a vertical direction, so that's supposed to be 60. That's supposed to be 30. Now we can start writing the components. E2x is positive or negative? Negative. Hypotenuse times sine of 30, so negative 16 times sine of cosine. I made it on purpose, so you would correct me, and you did. And negative 16 times cosine 30. I'm listening. That I know. $13? But okay, let's. Now we know components. What do we do now? This is what we are looking for relative to x and y components. This single equation represents two equations in one. And that is why we like vectors. We just treat each vector as a combination of two components. Now we can calculate, so 6 minus 13.8. 6 minus 13.8. Negative 10.5 minus 8, negative 10.5 minus 8. That's going to be 13 minus 6, 7, negative 7.8, negative 18.5. And now final step. These components represent that final vector we call net electric field. And now, if we know components, we can draw that vector. First of all, we need to extend the x-axis, the y-axis. X component is negative, so negative 7.8. Y component is negative, negative 18.5. So the actual net electric field points like this. Let's check our calculation. Maybe we did the magnitude wrong. The magnitude is supposed to be equal to this. It's always too good to have a check. And what was it? 20. We did it right. Whew. But now we can get the angle. Normally we measure an angle either just in a triangle, like this angle, we can call it theta. Or we might be told measure angle from like west to something or east to something. In physics, the angle would have been measured counterclockwise from positive x direction. It doesn't matter. As long as we know the angle inside that triangle, we can answer any question about any angle. And how do we get it? Well, I would use a tangent. The tangent of this angle should be equal to the ratio Ex over Ey, x over y, x 7.8 18.5. Theta is supposed to be the inverse tangent of this ratio. 7.8, 18.5. You should say it louder. If you say something, you should be loud.
22.8.
Thank you. 22.86, so 22.9, 23 degrees. And again, 90% of this problem is not physics, geometry. If you need to review it, welcome to office hours. We're gonna, the schedule has been posted. It's also on Blackboard. We have plenty of office hours. Use them. Any questions? So the similarity, big similarity between forces and the electric field is that they both are vectors. Net force is equal to the sum of all forces. And that sentence doesn't have any special name, but when we say the net electric field is equal to the sum of all individual electric fields, this statement has a name, the superposition principle. Superposition means overlapping or adding up. That's it, nothing else. Now you can finish homework, part one, and some people have it finished already, but some people didn't even start it. And I strongly recommend don't delay. I know you may think, especially if it's your first course, well, plenty of time ahead. I'm going to do everything during last weekend. No, you're not. Trust me. It's impossible. Watch the movie. Now, if we have a single positive charge and we want to draw electric field vector, we know the rule. It's an arrow which points away. Those arrows should be longer when we are closer, shorter when we are farther away from a charge. And very often, to represent the presence of electric field in a certain region, we don't draw many arrows because that takes too much time. We could have, but it takes just too much time. We draw electric field lines. One single line represents all possible arrows at all points on that line. And of course, the rule for the lines is the same as for vectors. The lines begin on positive charge and move away from it directly. And of course, we can apply the same reasoning for a negative charge. Well, actually, let's make it blue. A vector, another vector, another vector. If I don't want to draw all possible vectors, I can draw a line. This line represents all possible vectors. And for a negative charge, electric field lines are radial but point toward the charge. That's the picture. Now, we can use this reasoning to visualize electric field of many charges. For example, how would electric field of a dipole look like? A dipole is a combination of two charges which have the same magnitude but opposite polarities. So what should we do? Well, we should pick several points randomly and see how electric field vector would look at that point. For example, at this point P, we know what to do. Positive charge would generate electric field like this, a negative charge like this, and it should be shorter because this point is farther away. And now, how would a net field look like? Net field is the sum, like this, That green arrow represents the net field. And we could move on to the next point and the next point and repeat this procedure again and again. And we would get a line like this. It begins on a positive charge, it ends on a negative charge. In between, of course, it would be just a straight line, because here all vectors would have been pointing away from plus toward the minus, and weaker here, or no, stronger here. Yes, the strongest here. What about a line which would begin in this direction? First of all, if we are very close to a charge, so close that the electric field of this charge is the strongest, we can ignore the presence of any other charges. So if we are very close to this charge, electric field should look like electric field of a single charge. So like this. And here electric field should look like this. So, and the electric field line, that's a smooth line, well, it should just do something like this. How can I check if I'm right or wrong? Well, I need a way to measure electric field at any point I want to. For example, if I walk and I measure electric field here, it should point like this. It should touch the line, what we call it tangent or tangential. This is how electric field of a dipole looks like. And for any situation, we can use the same approach to draw electric field for 3 charges if we want to, 4, doesn't matter. There are rules which always apply. For example, electric field lines never ever cross. If they would cross, that means at the same point we would have 2 different net electric fields. That's impossible. Now, when electric field is strong, we can see more lines like per centimeter. And theoretically, some line might go infinitely far away to infinity. Yeah. But normally they begin on and end on a charge, begin on a positive charge and end on a negative charge. If we know how to draw several electric field vectors, we always can connect and draw a line. If we have a line, we always can draw a vector anywhere we like in this example. There is an important similarity between the gravitational force and electric force. We know the globe is a sphere. When we are far away from the globe, force of gravity points toward the center of it. We can see the direction changes when we fly around. However, when we are in Boston, here on the surface, no matter where we try to measure force of gravity, for us it always points straight down. A uniform gravitational force, or we can say field. That equation has exactly the same structure as the Coulomb's equation. The mass is just the gravitational charge. And if you want to calculate force over charge, G, this is just gravitational field. And based on this thinking, Einstein eventually come up with his general theory of relativity. Of course, it's a big leap, but it starts here. Now, for us, what's important is we also can generate a very uniform electric field. We just need something large and flat, like Boston. So if we have a very large plate, we put a charge. If it's a conductive plate, aluminum, for example, the charge will automatically be distributed uniformly everywhere. And if we're very close, in that case, no matter in which direction we walk, left, right, up, down, if we remain very close, we don't see the difference. For us, that electric field will be uniform. It will not be uniform if we reaching the end, the edges. In that case, we would observe the bending. But if we have a relatively large plate with a charge and we are relatively close to the middle point, electric field is uniform. And the strength of that electric field is related to the charge density, well, charge over area, charge density. This expression can be derived gradually from Coulomb's law. We don't have to do that. The only difference between a negatively charged plate and a positively charged plate is the direction of electric field. If the plate is positively charged, electric field lines must point away from it in all directions. What does word uniform mean? It means the same. The same in what? In everything. The same in direction, the same in strength. So, let's say we have two plates. Each has a charge. The magnitude of each charge is the same, but one is negative, second is positive. How would electric field of that system look like? It's not a dipole. A dipole, when we have one point charge and another point charge, and we know the field. Yeah. So, what should we do? Well, we should just analyze each field individually. This is a negatively charged plate. Just a minute ago, we said that first, we treat this plate as huge. Huge means it's so large that we don't really see the edges. And if that plate is so huge, electric field must be uniform. What does it mean, uniform? Electric field everywhere should point toward the plate. The density of electric field lines or vectors should be the same. And direction always toward the plate. That's it. Now we have a positively charged plate. What should I change? The direction. Well, since both plates in this example carry exactly the same charge, yeah, so four here, 4 there. Both plates carry the same charge. Electric field strength is supposed to be the same. And electric field vectors and lines are supposed to be directed according to the rule. And now what do we need to do is just literally add those arrows. It's about vector addition. So here, if we have like x-axis, this is the location of the positive plate, this is the location of the negative plate, and we need to add these arrows And we need to draw the result. Please finish this work. Please. This guy left. All right. I'm going to wait for him. Maybe next time. So for now, just finish the drawing on your own. Next time, in a similar situation, I'm going to ask you to use your smartphone. You know what for. They don't know what for. So, in the middle, between those plates, first of all, we always have to ask, what choices do we have? For example, here, what possible choices do we have? Well, we may have an arrow which points to the left, but has the same length as this arrow. We may have an arrow which points to the right. We may have an arrow which points to the left and longer, shorter, nothing all. That's how a brain works. It lists the choices, and then we should select those choices very often just by elimination. Oh, you're back. Please, draw the final picture. What do you think should we see for net electric field here, net electric field here, net electric field here? And everybody who already has that picture, please take your smartphone, use that smartphone to take a picture of your picture, and please email it to me. This is my email address. I know you already memorized it. So this is, we can call E minus. This is what we can call E plus. This is what we should call E net, or total, which is supposed to be equal to E minus plus E plus. Those are vectors, arrows. So you should draw something relevant, related to it, and take a picture. And again, I know that everybody has a smartphone. You don't?
No. Do you want a subject?
No. Why? I know what it could be. All right, I'm starting getting the pictures. So, vector addition, right? This literally plus this equals what? 0. What do we draw for a 0? Nothing. Moving on. This plus this is equal to, well, what choices do we have? 0 or not? If it's not 0, to the left or to the right? If it's to the left, shorter, equal, or longer? Twice longer. and here is 0 again. This is a very specific case which has a name, a capacitor. We have two plates, well, in general plates, but could have been something different like this. And we charge them up with opposite charges, usually of same magnitude. And in that situation, there is practically no electric field outside of that system. The whole electric field is condensed inside. And it's practically uniform, especially if we have large plates close to each other. Yes?
Does it matter that there's two blue arrows after the line? That direction is only one.
I'm not sure
So
what you're referring to.
the left of the blue colors, blue vectors. There's two of those. And then there's one of the red. Does that matter?
You mean two rows? I mean two columns.
Yeah. Farther left. There's two there, and then there's none directly to
What do you think? You asked?
I think if we're talking about magnitude, I would assume it does.
The key word is uniform. These lines represent a plate which looks small to us, but we have to force our brain into thinking about these as infinitely large plates. In that case, electric field must be the same everywhere. So if it's 0 here, it must be 0 everywhere on the right side of this plate. If it's doubled here, it must be the same here between. And if it's 0 here, it must be the same everywhere. That's it. Of course, it's an approximation. We know in reality, it's not exactly the case, but it's an abstraction. A good, simple abstraction. And if we want to calculate the strength in this situation, the net field will have the magnitude of doubled, you see? We just, this coefficient is just a fixed number. It's 1 divided by 4 pi k. We could have used a pi, but in that case, we would have used 4. We could have used a k, but in that case, we would use 4 and pi as well. So it has a special name, which doesn't really have any meaning anymore. It is just a number. The letter is epsilon, epsilon naught. And this is how we can calculate the total electric field inside a parallel plate capacitor, which we will in the future. Right now, it's just an exercise in adding vectors.
What's the A in the equation?
Area. In reality, no plate is infinitely large. In reality, every plate has a certain area. In reality, Q represents a charge stored on that plate, and A represents the area of that plate, wherever it is, square, circle. Question. Now we have a dipole placed in the uniform electric field and released from rest. What might happen? What choices do we have? Well, nothing or something. If something is happening, what choices do we have? It might move in a certain direction, left, right, up, down, or it might spin in a certain direction, left, up, right, down, counterclockwise, clockwise. In this situation, of course, we need to start from drawing forces. So This is an exercise on this equation. Twice. Let's start from a positive charge. That's the positive charge. The electric field points to the right. That means the force acting on this positive charge points wrong. For the positive charge, electric field and electric force always point in the same direction. For the negative charge, they point opposite to each other. So the electric field points to the right. It's the same everywhere, uniform electric field. That should generate a force directed to the left. Now we're adding something which holds them together, a rod, a fixture, and release them. And what should happen? First of all, the net force is equal to 0. Two forces, same magnitude, opposite direction. Net force is 0, which means it can't start moving away in any direction. So if net force is 0, the next thing to think about is net torque. Review. Is net torque equal to 0? No. It actually counterclockwise. So it should start spinning counterclockwise, maybe with a certain acceleration, angular acceleration, if nothing else is acting on it. Yes?
I thought that if you had a positive charge, it would move away. I was thinking the arrows, my vectors, the other side.
What can I say? You thought wrong. We need to divide the brain into different cells. One cell should be responsible for electric field acting on a charge. Another cell should be responsible for electric field generated by a charge. Those are different things. This electric field is being generated, but we have no idea by what. It could have been a positive plate located somewhere here. And these electric field lines point away from that positive plate, and then they hit the positive charge and start acting on it. And this charge now feels, experiences the force from those charges via electric field. So technically, we could have imagined a positive charge on the left, which repels this positive charge and attracts that negative charge. We can use this phenomenon to visualize electric field. Visualize means what? Make it visible. But to make it visible, first we have to kill this. I've been dying to do this demonstration since yesterday. You're not lucky today. This demonstration has a name, grass seed viewer. Here, in a plastic container, I have grass seeds. I don't know what kind of a grass. I don't care. In oil. Each grass seed can move in oil. If we apply electric field, that electric field will first it starts polarizing those seeds, like in demonstration with a bat and a wood. Polarization starts happening, and those seeds become dipoles, and they start turn because of the torque. And that tells us they align. Well, if everything works today, it worked in the morning. I have a witness, but it's been sitting for a long time. This machine might become, again, too humid, too wet. This machine has a name, a Whimpers machine. It's based on a principle: if you rub things together, the charge is being generated. There are some brushes here, and these, well, Leyden jars, capacitors, can collect some charge. First, I want to check if we actually can have any charge here. Oh, we do. When we have enough charge collected on in each capacitor, they can make a spark. And now all I need just you don't want to be shocked. It's not deadly, but still, it's nice feeling. So what do? It's a conductor, a copper wire. It lets electrons to travel in any direction. I can use these wires to bring the charges here. I don't know which will be positive, which will be negative. It's randomly. So one will be positive, another will be negative, and we should observe electric field in between. Let's hope it works. Okay, I can see some movement in the middle. So you can see the lines formed by those seeds parallel to the electric field lines. Let's see a uniform electric field. Seeing is what? Believing. That's what magicians like to say. All right, I have to fix the belt. This is a very old device. Not 100 years old, but still. Oh, even better. I think I killed my computer. If the spark is strong, electromagnetic pulse actually can influence your phones and computers and USB devices. So what I see here, practically uniform electric field between two parallel plates. That's what we call a capacitor. And for one of the next lessons, let's try this one. This is a circular capacitor. Oops. A circular capacitor. And let's see. Okay, my belt is still on. All right. You see that the alignment is happening between these electrodes, but nothing is happening in between. The electric field inside is zero. That's what we call shielding. If you have a closed conductive surface, like a car, electric field cannot penetrate it, cannot go inside. Well, I'm here. I forgot, I have one more slide about, so, do you know the question? So what do? You go to the website, get prepared. This device has a name, Van der Graaf generator. You can Google it. It's also based on a principle of rubbing. Here there is a belt, rubber belt, which rubs against the plastic cylinder that separates charges, and those charges can be collected. And let's see, I haven't checked it today actually, so it might not work. Fingers crossed. Oh, it does. That's a nice surprise. Also, I want to discharge it. Now you can answer the question. Later. First, you should answer the question. Oh, I see the question. You can see the question. Now you can see the question. So, what did you say? Did electric field do a work in this experiment with the Van der Graaf generator? That's a yes or no question. All those destructors, irrelevant. Even if you don't like this question, you can't answer 6. What did you say? Yes. Now, what happened? Very simple. Each peanut initially is neutral. When we start running the generator, this dome starts charging. People say normally it's negatively, but again, it might be random. It doesn't matter. Let's say this dome becomes negatively charged. So those electrons don't stay here. Yeah, that's aluminum. They reach the peanut. The peanut becomes negatively charged as well. And now 2 negative charges repel each other. And they strong force of Coulomb repulsion makes them move away. Without gravity, they would be just traveling straight ahead like this. We actually could see that, they started moving radially because the electric field, this is like a spherical charge, electric field points like this. But of course, gravity starts acting and eventually they fall. That's it. And the work is done because, as we know, the work kinetic energy theorem tells when kinetic energy changes, work must be done. Rest means no kinetic energy. Motion means kinetic energy. From nothing to something means change had happened. That's it. It means we need to start talking about energy, work. We have to refresh what we learned about it. And this is some of the most important things which we have learned. There are different types of energy. Kinetic, which is mv squared over 2. Several types of potential energy we've learned. mgh, gravitational, kx squared over 2, elastic, and today or tomorrow there will be one more type, electric potential energy. Mechanical energy, that's what we call the sum of kinetic and potential. And when kinetic energy changes, work is done. And if a force does a work which can be found as a difference between initial and final values of something, that thing has a name, potential energy of that force. So this is a blast from the past. This is an analogy which very useful to remember and to use. If we have an object, we move it up against the force of gravity. We do positive work. Gravity does negative work. If we let it go on its own, if we release an object, it always starts traveling from higher potential energy to lower potential energy. High, low. Same is true for electric field. So let's go through one specific, simple situation. Uniform electric field, a positive charge is released from rest. So a uniform electric field means the same everywhere. We should assume it's happening in the outer space, so nothing else is acting on this charge. Now, these vertical lines represent electric field which might have been generated, maybe positive charges above it or negative charges below it. Doesn't really matter. All we know is electric field exists and uniform. If I release this charge, it's going to start traveling because of the force acting on it. So these lines represent electric field, and the electric force acting on this charge is related to the charge and electric field. That is how we know that eventually it reaches a different location. So this will be the distance traveled or the displacement. And for a uniform electric field, the force acting on the charge remains constant, uniform. And for a work done by a constant force, we have an equation. The work done by any constant force is equal to the product of three variables. The magnitude of the force, the magnitude of the displacement, and the cosine of the angle between the force and displacement. In this particular case, the magnitude of a force is equal to this. The magnitude of the displacement. Well, now I want to introduce an axis and a rule. A rule means you got to memorize it, put it in your memory cell. Draw the axis parallel to electric field. If the field points to the right, draw the axis to the right. If the field points to the left, etc., etc. In my example, electric field points down, which means I have to draw the axis down. And this is my origin. This is my x initial. This is my x final. So how can I write the displacement? X final minus x initial times, what should I write for the angle or for the cosine of the angle? How does force point? Force, how does it point? The force, F, down. How does the displacement point? Down. If two vectors point down, what is the value of an angle between those two vectors? Think again. 0. So again, that's a review. a vector of a force is down, a vector of a displacement is down. There is no angle between those two. Theta is 0, cosine of theta is 1. And now this is how people rewrite it. Why? Because people want to look at it as something initial minus something final. Why? Because if a work of a force can be calculated as something initial minus something final, that thing has a name, potential energy of that force. That's it. That is actually an official definition of potential energy. So, moving on. This is the summary. You can read it. Electric field does work. Of course, it could have been a negative charge. A field could have been differently directed. As long as electric field is uniform, access points parallel to the field, we can always write an equation for potential energy of a charge in that field as this. And more importantly, the work of electric field is equal to difference between initial potential energy and a final potential energy. This equation only works for a uniform electric field under these conditions. That equation is universal, works for any electric field, any charge. That's what's good about it. This picture shows what would be happening with a negative charge. Of course, it would be traveling in opposite direction, but of course, it would be, if released from rest, would be speeding up. Kinetic energy would increase, work would have been done. So, what's to remember? Any charge placed in any electric field has that thing we call potential energy, which is related to work. If charge has been moved, for example, from one location to another location, maybe we did some work, maybe, but electric field definitely did some work, and it is equal to this. And this is handy equation we will use again, or kinetic energy theorem. Question. Last question for today, I promise. And the answers to this question interest me. So, okay, first switch from a pen. Let's go to Whimpers, resend. So, the question: a positive 1 coulomb charge is placed at a certain point, and someone told us, or we have measured its potential energy. Turns out 10 joules. Now we move it away, and we place a positive 7 coulomb charge at exactly the same location. What do you expect to be the potential energy of that charge? Well, if you answered 1, 2, 3, 4, 5, or 6, you should ask yourself, why? Energy, like mass, additive. Basically, you're adding 1 coulomb at a time. Starting from 1 coulomb, when you add 1 more coulomb, it gives you 10 more joules of energy, 2 more coulombs, 2 more joules of energy, etc., etc. So, if we have a value for, well, people use, as you have noticed, capital U for potential energy, or in this situation, it's not elastic potential energy, it's electric potential energy of a 1 coulomb charge. You can calculate the potential energy of any charge by just multiplying by the number of coulombs. That would have been potential energy of that charge. But because of the importance of this particular energy, the energy of a positive 1 coulomb charge, because of the importance of this, it's been called a special name, and we have reserved a special letter. The potential energy of a 1 coulomb charge placed here has a name, electric potential. It has energy potentially. And the relationship between this new variable, this new name, electric potential, and different people use different variables, different letters. So this capital V doesn't represent volume or speed of Voroshilov. It represents electric potential. And if we know electric potential and we know a charge, we can multiply these numbers, and that gives electric potential energy. And good thing about electric potential, we actually can measure it. It's much easier to measure. We can go to Home Depot and buy a measuring device, multimeter. But this is an official definition of electric potential. If we have a charge which is filling, not generating, is being placed in electric field, and we know the energy of that charge, for example, we know how much work has been done to bring it here, the energy of that charge divided by the actual value of that charge, that's what we call electric potential of electric field at the location of the charge. And again, people don't say the whole thing, they say potential. And we need to understand, in this context, this word means the electric potential of electric field acting on this charge placed here and now. That's what it means. Well, one more. Yeah, that's what I wanted to say. In this equation, this variable doesn't represent a magnitude. It represents an actual value. For a positive charge, this number has to be positive. For the negative charge, this number has to be negative. And we also remember from the past, potential energy also can be positive, negative, zero. Potential energy over a number means potential, electric potential, also can be positive, negative, zero. So this product can be positive, negative, zero, anything. It all depends on specific situation. This is what we need to remember. If from the previous slide, with the introduction of electric potential, we can relate the work to charge differently. For example, this equation, initial potential energy minus final potential energy, But also, in the past, we had an equation this equation, same work. So if we write these two equations together, like here, we can derive a relationship between electric potential difference and electric field strength. The charge disappears, getting canceled. To derive this equation, we've used an expression from a uniform electric field. But we know that if we take two locations pretty close to each other, we can treat electric field as almost uniform. So we can always use this equation to relate two potentials, the distance between those 2 points, and electric field strength between those points, assuming it is almost constant. We just must remember that, first, both points should lie on the same line, not on the different lines. And, well, I'm going to go through this tomorrow again, but electric field line always point from a higher potential to a lower potential. Like imagine electric charge, positive charge released here, it should be traveling along the field from high potential energy to low potential energy. So does electric field point from higher potential to a lower potential. These are rules. This is not a question. Again, a note, terminology. In physics, when we say a word change, it always has exactly the same meaning. It's a difference between the final value and the initial value. In this experiment or example or wherever, we moved a charge from potential number 4 to potential number -8. Of what? An official unit for electric potential is volt. So the same letter, capital V, also represents the unit of potential, volts. 4 volts, -8 volts. It doesn't matter what charge we use. It matters what point is being initial and final. So to calculate change in the potential, we have to subtract correctly. -8 final minus initial, -12. People also say difference. In our class, the word potential difference always means the magnitude of change. And also people say potential rise or potential drop. We say potential rises if initial is lower than final. And we say potential drops if initial is higher. And that's all I want to say about it. Thank you. And now you're going to be able to solve a lot of problems. From part two, yeah, a lot of problems on energy, work, electric potential can be done now. And I'm going to pick up from this tomorrow.
Yeah.